So in our next section, we are going to talk about theoretical probability. So it is not always feasible to perform an experiment over and over again in order to calculate empirical probabilities. It is possible to calculate probabilities without performing an experiment at all using theoretical probabilities. So our definition for theoretical probabilities is based on theory rather than experiments. In order to be able to do theoretical probabilities, there is an assumption that you need to consider. It is that all of the outcomes in the sample space need to be equally likely outcomes. So they all have the same chance of being, if the coin is flipped, there's a, half chance that it lands on heads, half chance it lands on tails, so they're equally likely. So how we calculate theoretical probabilities? The first thing is we want to count the total number of possible outcomes. We can also write them out, right, with our sample space. Step 2 is to consider all possible outcomes and count the number of ways the event of interest, let's say call it A, can occur. Step 3 is to determine the probability of A, or P of A, using the formula. So my numerator would be the number of outcomes in the event space, and the denominator would be the number of outcomes in the sample space. So let's look back at our single die experiment. It says, by calculating all possible outcomes that can result from the experiment of rolling a die, we know the theoretical probability of rolling a 5. So if I think of a single die experiment, right, we could say, event A, or all my total sample space, right, my sample space would be 1 all the way to 6. Right, those are the possible outcomes when I roll a die. Now the theoretical probability of rolling a 5, right, there's 1 5 out of the total 6. So we would say the probability would be 1/6. Now let's just note that the empirical probability and the theoretical probability will not always be equal, especially if you have such a small number of experiments. But if the theoretical probability is correct, as the number of trials increases, right, so we repeat the experiment more and more frequently, we talked in the last section, right, we repeatedly roll this die, the empirical probability should become close to the theoretical probability. In probability, we call this the law of large numbers. So yes, the more and more times you do an experiment, the closer it gets to this theoretical probability. So let's just calculate some basic theoretical probabilities. So A says, find the probability of drawing a queen from a standard deck of cards. So if you're not familiar with the standard deck of cards, it is something used a lot in probability. So you can always Google a picture and see sort of what the standard deck looks like. We'll talk a little bit more about it in the coming pages, but we have 52 cards in my standard deck, and there are 4 queens. So the probability of drawing a queen from a standard deck would be 4 out of 50. So let me show you a couple things on our calculator. So 4 divided by 50, right? So I can get a decimal. If it needs to be a reduced fraction, your calculator actually reduces it for you. If you hit your math button and it's already selected the one we want, if we hit enter and enter, it will reduce it as a fraction. So whether you need it as a reduced fraction or if it wants it as a decimal or percent, sort of depends on what it's asking, but we can find all from our calculator. All right, it then says, find the probability of meeting someone with a phone number that ends in a 1 or a 2. So let's think about the possible numbers, right? It could be 0 through 9, right? And if I listed them out, right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's my sample space. And if I actually count the number of outcomes that I have, it would be 10, right? So there's 10 numbers that are possible, right, that could end this phone number end with. So the probability of a 1 or a 2, well, there's, right, this would be 2 out of 10, or 1/5. Or again, if it wants it as a decimal, this one doesn't really state, so I'll just sort of show you all the possibilities, right, 0.2. All right, so then it says, find the probability that a randomly selected person has a birthday in June. So, probability of June. So if I think how many days are in June, right, there's 30 days out of my 365. So I could take 30 divided by 365. Let's round this to a decimal. So roughly 0.082 would be the probability that the person's birthday is in June. Now, D says, find the probability that a randomly selected person does not have a birthday in June. So if we know that they have a birthday in June, write that probability that does not, there's a nice formula that we can use. And it's a complement, this idea of what's sort of like the opposite. So the probability of not in June would be the 1 minus the probability the birthday they are in June. So, and this is called the complement. So if I take 1 minus 0.082, so 1 minus 0.082, we would find, right, roughly 0.918, oops, sorry about that, 8, let me erase that. Oops, there we go. So you can see a little better. 1.918 would be the complement. So it'd be the probability they do not have a birthday in June.